All right, I should be on screen now. I was a little bit in the back end there, guys. So welcome again. I'll do a quick, brief intro again for the people that are just joining us now. So we are going to be listening to a presentation on decarbonizing domestic hot water using CO2 heat pumps. Kashif Muhammad, he is the sales manager for commercial systems in Ontario at Mitsubishi Electric. He will be presenting today on our chosen topic. So thank you so much, Kashif. Go
Thank
on
you.
ahead.
Thank you very much. Let's start with the presentation. Today we'll be covering the decarbonization of hot water, domestic hot water using CO2 heat pumps. This is a new technology that's coming up, and we're getting more and more of those applications as the time moves on. If you see an average Canadian household uses approximately 75 liters of hot water, may it be for washing dishes, clothing, cleaning, showering, and bathing. So to use this 75 liters of water, we need an approximate energy of 17.2% that is used to provide a hot water for domestic use. So, how we can create this hot water is been traditional way of doing the hot water. That is, you use the boiler, use a gas burns and burns. It provides hot heating to the hot water that would be used for uh, multiple applications. Um, what are the advantages and what are the consideration using those kind of things? Like first thing, since we are using gas to heat the hot water, so it's a fire and exhaust gas. We need to maintain those things. So that's a consideration of safety. We need to take care on those things. Efficiency, since the gas heating is not the best efficient, the max you can do is 100% efficiency. So, and and it does on and off depending on what loads are there. So you can consider. I mean, if you want to give rating to the uh, efficiency, you end up using a two-star rating for efficiency side. Maintenance, again, since the gas is involved and the exhaust is involved, you need to get some proper maintenance people that are trained specifically to handle gas heating, and you are required to do periodic inspection to your gas facility to make sure it doesn't leak and it doesn't provide any harm. Yes, and the cost of installation, yes, it's much easier, and since it's easily available in the market, you end up using those equipment quite easily without any issues. And as we know, since we are burning the CO2 to get, since we are burning the gas to get, and your byproduct is one of the product is CO2, so it's CO2 emission is one of the major issues using the gas boilers. So if you're moving to, I mean, the alternate solution that is going for the hot water using electric heating, yes, you are good using electric heating because since this is no gas, your safety is not much of an issue. Again, if you're using electric heaters, you can do 100% max efficiency on those things. So again, if you're giving star rating for those efficiency side, you end up going providing a two-star rating for electric heating. Ease installation because there is no gas fitting involved there, so you may end up having higher efficiency. And again, though you are not burning those gas at the facility, so you are better than a gas boiler, but still, since it's not efficient compared to the heat pump side, you may end up having a more of a medium kind of efficiency or medium CO2 rating. Yes, the solution, which I mean is prevalent and it's getting more and more traction these days, is use of heat pumps. Why heat pumps is more efficient and more practical now coming days? Again, we are not using gas. It is efficiency wise, it's much more efficient. You end up 3 to 4 times more efficient than electric heating. Maintenance wise, no gas means it's easier to maintain. Installation wise, since it's a system, it's a different type of system, so you may need a storage facility that's good enough to handle those peak hours, which we'll be discussing in coming slides. So that installation wise, you may end up having more more time and more resources spent on this one. And again, since we are using a high efficiency machine, so your emission is low compared to this one. So you may end up at three, five high size rating on this rating. The refrigerants available in the current market that are HFCs, we may having R10, R4 404, R410, R134, R32, CO2 is the best among those things because we are having it rise in the group A1 and it's having a GWP of 1. So if you compare it with all the available refrigerants, you may end up having a best solution compared to if you're using it. CO2 is a natural solution if you're providing hot water to your domestic use. It because it's a low carbon solution and it is suitable for portable application. If you why it is a suitable application, it helps decarbonizing the building because it is using a refrigerant that is CO2, which is having ODP of 0 and GWP of 1. Typical application using hot water produced by CO2 heat pumps is a healthcare facility, hospitals, old age facilities, and educational institutions where you are having a high demand of water at different peaks of time. Why we say the COP is the best solution compared to other things. So what is happening in a CO2 application? You are using 1 unit of electricity and you extract 3 units of heat from the environment and we provide a result that is ending up 4 units that could be used for heating purpose. So that's why we say it's a 4 COP. So we are putting 1 unit of energy to run the machine and extracting 3 units from outside and providing out 4 units in total to provide hot water. This technology is not new. It's being used in the industry for quite some time, more than 50 years. Started in Japan around 70s for domestic water use, and it's a reliable technology. But since the focus was not much, so it was not marketed by the different suppliers. Now the trends is happening, and the we are getting more switching towards the decarbonizing efforts. So this technology is the future coming for this. How it works? It's a quick way. The water flows. It uses a specially designed spherical coil in which the CO2 circulates on those spheres and the water flows inside the coil or inside the pipe kind thing, which is spherical. These are specially designed spherical shapes which increases the contact between the water and the CO2, makes it more better heat transfer. And other than this one, it is also creating some turbulence which helps the heat transfer of this. A typical application where you are using water comes inside your facility. It goes at the bottom of the tank from where the pump circulates it in a secondary side. It does a heat exchange with the hot water that's produced by a CO2 heat pump, and you get a hot water which is stored in the pump, and this hot water is used in for domestic use. You mix it in the faucet and get it required temperature. Let's go a little bit on how CO2 works on this thing. So CO2 is working on a higher temperature and higher pressure level. So it can provide you up to 80 degrees centigrade of hot water that can be used by for your domestic use. Let's move to a typical pH diagram where our compressor does a work, increase the pressure and the temperature, and when you come, the water comes in contact in a heat exchanger. It gives its energy to the water, and once it is there, let's say the water coming at 55 degrees centigrade, it stops here. We get an expansion, and then it goes back to the cycle. So this is a typical cycle where your compressor does the work, and you do a heat exchange using a water coming from source, and then you do expansion and go back to the compressor. So if your water is coming around 55 degrees centigrade, That will be your energy that you can extract it. But if you're looking for the same compressor work and your water inlet water temperature is around 10 degrees centigrade, you may be having a better heat transfer. Now, what's happening there? Instead of water coming at 60 degrees centigrade, where you stop your process here, now you are running more of the heat exchange process in a heat exchanger. So you, with the same compressor work, you are having a higher output. That's a hot water. So in these kind of application, it's preferred, and it is defined as a machine that would do a high delta T but low GPM because your capacity is constant on this thing. So it's just a quick comparison. Again, your compressor does the work, and if your water is at lower temperature, let's say 60 degrees centigrade, you get this much output from the system. But if your water coming at 10 degrees centigrade, a lower temperature, you are doing more output from the same work done by the compressor. On a domestic water side, we there are basically two categorized in two basic types of domestic water system. One is low recovery and high storage, and second one is high recovery and low storage. A quick difference between two: the low recovery machines, it stores high volume of water, and uh, and it has got low rate of recovery. Like means the source or the power or the hot water done by the machine is low uh, compared to the high recovery machine. So what it does, you have got a high volume of water stored, and you do a large draw for short period of time. So it comes in small time periods where your demand of the water is more, and then you provide it, and then you end up doing it for the next cycle coming. We'll see in the coming slides how it works. So, and the second one is a low volume storage and high recovery. Your machine or the boiler or the one which provides the hot water is a larger size compared to the volume, and it is usually applicable when you are looking for instantaneous heating demand, or where your demand of the hot water is constant. It's not changing at all. So you prefer having a high recovery and low storage machine. A typical application for high volume application is a multifamily, senior living, hospitality, uh, higher education, gyms, commercial buildings, etc. etc. A typical hot water usage for different facilities. If you see here, uh, um, for a business hotel, you start in the morning, your demand, people wake up, start taking shower, bath, and everything. Your demand goes up, and let's say up to 9 o'clock, you have a high demand. Then demand started going down, 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 and then you have a small demand between like 12 to 3, and then it's no demand, and then you end up having after 4 o'clock something you have demand. So what's happening there, you have a demand coming up, down, and come, so your load is not constant, and and you have a peak and demand where you end up having hot water required for high demand of volume, high volume water required for certain period of time. How generally it works, you have got a cold water coming at the bottom of a tank, this city water, and you connect this tank, storage tank, to a heat exchanger through a pump, and this pump circulates depending on what temperature you set it, and it does a heat exchange from a primary source, that is a hot water generator or CO2 heat pump. It do heat exchange, and you get a temperature which is set like 60, let's say 65 degrees centigrade, which is used by the facility, and you get a hot water for the facility. How it works, I mean, you have an option control of, philosophies. You can have multiple sensors installed in your storage tank. If you're looking for large demand of water, you can set your temperature that, okay, I want my temperature to be of T th16, to be set to 65 degrees centigrade. When my temperature of the tank at TH16 is 65, you shut down the machine. And once it goes lower than this one, you start the machine. So depending on your control philosophy, you can set it. If your demand is very less, you can set the same thing for your TH15. There's a higher level transistor transition that would sense, or temperature sensor that would sense the temperature and give the command to the um, hot water machine to shut down or shut off. How we control the temperature of the living water, depending on, there is a sensor installed on secondary side which sense the temperature. Let's say we put a temperature of 65 degrees centigrade coming out of this heat exchanger. So if your temperature sensed by this temperature sensor, it says that I am less. So what it does is this machine gives the command to the pump to slow down or ramp down to make sure there's a proper heat exchange happening there and we get a required temperature, and vice versa. If you're getting like a higher temperature than you set there, so it will ask you to ramp down, move slowly, and to get the required temperature. So to correct to vary the flow, you have got two options. You can go with a constant volume pump with a two-way valve that would operate and make sure that you maintain a certain amount of flow on the prime secondary side, or you can have an inverter-based pump that would modulate depending on what temperature is sensed by the secondary sensors. A typical application, again, coming back, you have got a hot water generator or a CO2 heat pump that provides hot water through heat exchanger to the tanks. You have a sensors depending on what temperature you set it there. And but again, these in the beginning we have seen that there were uh, these machines were designed for a high density application. So if we try to recirculate this hot water back to the cycle, it will decrease the efficiency of the system. So it's not recommended to use like a hot water going back for recirculation. To cover this thing up, there's a swing tank that has its own electric heaters available there. So anything which is happening, like coming back from the recirculation side, we the electric heater will maintain the temperature set for the facility. So electric heater in the swing tank is there to compensate or to maintain the temperature that would be going to the building. On the storage tank, it is recommended the tank should be a vertical type, not a horizontal type, because we want to maintain a stratification. That's the most important aspect of this one. Stratification will be happening there in that your temperature on the bottom side will be low because the cold water is from the city is coming at the bottom. Then because since the hot water is coming on the top, so there will be a, let's say, a 160 to 140 temperature coming at the top, and 120 to 140 coming at the mid size, and again from the bottom, since the water is coming there, 41 to 21 120 Fahrenheit. Again, moving back to our cycle. So these are these yellowish are the demand, and that one is the pink one is the production line. So what is happening there? You run a machine continuously, and you till you're like I say 17 hours a day. This machine running has no direct correlation with your demand load, because what's happening there, you are using this CO2 heat pump to charge the tank which is supplying hot water to the facility. So these peaks, yes, but when we are designing our system, we have to make sure that okay, these peaks are met and your storage is good enough to meet those peaks. That's the intent of this one. So that so if you see the water coming there or water there, you've got a demand. It water is going down, then you charge the system. Then you meet your demand. It goes down, and then you charge the system back again to meet your demand. So So again, this the storage is the key in this typical application, where your machine, we want to run it maximum time, like 16 to 18 hours, to make sure that we get a required hot water, but in our tank, which is charged by the machine, and the tank is the one supplying the hot water to the facility. Again, coming back to this one, this is the typical temperature of the day. So we the demand has no direct correlation with the temperatures also. So we'll notice that, okay, uh, when we are running the machine, let's say, we want to we when we are running the machine, that's a 17 hours. It's not necessary we run it from there, like hour 0 to hour 17. We can switch this operation from here to there, depending on if we are looking for something, using the energy rates, we want to take an advantage, or if we have a facility, or if we have a temperature which is below the operating range or very low, we don't want to run it on this particular thing. So we'll see in the coming slides how it's taking care for those things. That's that's a typical building in Ontario, with a 204 units as simulation of the data which is happening there. So this is 2023 weather data for Toronto. So if you see here, our operation or our temperature most of the time, like the max 2 or 3 hours, it was in between minus 20 and minus 15, and there was no minus 25 and minus 30. Yeah, there will be times there, for coming years, or there will be time that your machine or your ambient will be like there will be few hours there. But in generally, if you see the operation, the most of the operation is a very safe, let's say minus 5 to 40s 40 centigrade. So again, moving back to our example, it's there, in this apartment building. We say there's a 48 studio apartments, one bed apartment 40, two bed apartment 82, and three bed 34. So we, based on our criteria, we saying that there are 442 occupants in the building. Based on, again, 25 gallon per occupant, we will be needing around 11,000 gallons of water for their domestic use. Uh, Considering that, okay, water is coming in at 10 degrees centigrade, and we want to raise it to a 60 degrees centigrade. So with this, we will be having a total energy required for hot water use 884 kilowatt for 1 year. So based on the temperature profile which we've seen earlier, we 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 don't want to run our machine on the lower temperature. So if we are running from, let's say, 10 to 40 degrees centigrade, we are meeting our demand, our hot water demand. So and we are operating on the average 16 hours a day, this hot water generator. So if we are preventing use or running of the machine in a temperature which is lower, where our COP is not the best one, we are having a very high efficient system that's around producing around 3.8 COP. So that's a very advantage. But again, what generally when we are considering and we are reviewing our design, we take the worst scenario and say, okay, this machine is not efficient. But again, we are not running the machine on a specific temperature, and we have a liberty of using or running on a preferred temperature. So since we are not providing direct hot water to the building, we are charging our hot water tank that is supplying the hot water to the building facility. Again, if we consider in terms of based on electric heater, gas-fired boiler, and CO2 heat pump, you have a substantial uh, uh, reduction in CO2 emission compared to gas-fired. That is obvious because we are running a lot of gas there. But even compared to electric heating, which is 1:4 magnitude, which is shows that okay, it's a 4 COP on our side. In general, we can do how we size a particular hot water system. Um, like it's a computer software we call Ecosizer is the mainly is commonly used in the industry now, but there are others modified Hunter curves and recovery versus storage and average demand methods. I mean there are different methods used by different in different scenarios by different engineers. I'll, so like Ecosizer is the one that is most commonly used. Again, we are running our Ecosizer based on the data provided. We are looking for a heating capacity of 556 kBtu per hour and a storage tank as mentioned here. And if you're looking for recovery versus storage method, there are different facilities having a different types of curves, which is suitable for us. Like our example is an apartment building, so we'll be using our apartment building curve in here. So we start with like a 204 units, and we say it's a two full bath and kitchen and dishwasher there. So now our thing, we start like we start a reverse way. We say, okay, we are using our 400 gallon of storage for a 204 uh, apartment building. Means that we are using our 2 gallon per apartment number to size our recovery thing. So with this one, we end up around 833 mph of recovery machine. Similarly, if we think other way around and we increase our size of our storage to a larger one, let's say 5,000 gallon. So based on 204 apartment building, we are using around 26 gallon per apartment, and based on this particular thing, we may end up around 448 gallon per hour, or capacity is around 375. So if you see here earlier with the smaller size storage, we were using a higher capacity or higher recovery. Comparing it with this larger size tank, we are using a smaller recovery machine. So means that if we increase our storage to to certain capacity, certain limit, we may end up using a smaller size machine to produce heat source. There are other ways. Typical again. So when we are designing our system, or we are considering using a mm, domestic hot water tank that can provide hot water for a building. So we need to see what's best for us. We either want to go for thermal storage strategies. We want to do a best thermal storage option available. It will help us reduce the size of the machine, and and we have to make sure that we are able to provide uh, required hot water for those peak demands. So our storage capacity should be good enough to help it out on those things. And either we can use the time of use electricity, means that okay, if your temperature is not very uh, um, low, you can use it. You can charge your tanks at the night time where you are having a better energy rate. Or other way around, if you think that okay, your temperature is very low and you don't want to run your machine in the low temperatures, to make sure it is running very efficiently, you can use it other way around, depending on your application where you end up. A couple of examples where or case studies where we have used those CO2 heat pumps. It is one of Hotel Marcel, New Havens, Connecticut. It was basically a rubber factory in done in late 1967. Um, then it worked, and then it was abandoned. It was not used, and the developer want to use this space to get to build up a hotel. So the engineer worked with them, and they said, why don't we repurpose and reuse this already existing structure? So they did re-engineering, and they use an existing facility, existing structure to provide uh, to convert it into a hotel that is passive house certified, first hotel in North America. It is using solar panels, and it is not having any of gas or natural gas coming into the building. So it's solar panel, and for the backup they are using electric batteries. So if in case there's like some requirement on emergency basis, the electric battery can work it out. So and this facility is having kitchen and laundry all electric, so they are not using any hot water that is done by natural gas. So it's a 165 room hotel. uh, Total area is 110 square feet. That's an old building picture, and now it's one of the boutique hotel in this one. And what they did, they used a three CO2 heat pump to provide hot water for the kitchen, they and their laundry. Again, it's the first net zero hotel in US. So what advantage we got it from there? It's because since a CO2 heat pump compared to electricity is much more efficient. And what we are using, it's an existing building. We use CO2 to provide hot water, so we are reducing the carbon emission. And it was considered as a net zero facility, and it was certified as a first passive hotel. Another project, it's a 100 unit low income multifamily facility. It's a 13-story building where since it was initially with electric boilers, and they, they they used a CO2 heat pump because it requires a lot of it requires a proper setup, means that you need to have storage facility on for the water to be separated, distributed among to different apartments. So, and the facility was already occupied, and everything was there. So what was done? They used a skid mounted solution where they have provided a heat pump that is providing a hot water, and it's a built-in skid. You got a storage tanks and, and required accessories like pumps and everything. So it's a one point solution to provide hot water to the building. There was again this was single heat pump was used in this one, and it's supplied at prefabricated skid assembly.
Can I interject for a second? We do have a question.
Oh, that's good.
So we have a question from Glenn. He's asking, can this unit be set up inside a building and use both inside and outside air?
No, no, it is not designed since it's a CO2. It is not recommended to be used inside the facility. It has to be outside because it's a high pressure machine. So it's recommended to use it outside.
All right. Thank you.
Yeah. So I mean, using since it was initially again it was an electric facility. So I mean, there is a reduction of power usage. So around from 230 to 95 kilowatt happening there. There was a to convert it into the electric rates, and you end up around $15,000 annually on the building cost saving. And it's again, since it's a heat pump, on the average, you they were having around a COP of 3, means that okay, you are reducing your power input to one third, or if you want to look at other way around, the same power input, you're getting three times the power on, output from there. There is another project here in Japan. Again, they were using three of those CO2 heat pumps to charge um, those storage tank, which was supplying hot water to the facility. But again, what they did different in here, instead of using electric heating to maintain the temperature of hot water, to maintain hot water for swing tank, they use another heat pump that is not a CO2 but A12 based machine that is maintaining. So again, that helped them further reduce the electric consumption, because again CO2, it's a A12 heat pump is also having a better efficiency compared to um, uh, direct electric heating. It's a four-story building. It's a large facility, around 4,000 meter square. With the it's a 30 guest rooms were there, and it's operational like it's since 2014. So it's working for quite some time. That was a quick one. Yes, please.
All right. Oop, I'm back in. All right. So that was everything. Wonderful. Thank you so much, Kashif, for that amazing presentation. Sorry, I'm just being distracted by the telephone ring. Thank you again. If anybody else has any more questions, now's the time to ask. We have a bit more time in this allotted time
Yeah.
slot, so feel free to fill up the chat with lots of questions. Or this is your last chance. I'm going to give you guys a few more minutes.
I was anticipating more of a question, so I kept like it's a smaller one, so that it'll be more of interaction. So yeah.
I mean, if anybody has any questions also following the presentation, you have more than welcome to reach out to Kashif yourself, and he will, I'm sure, answer any questions via email as well. If you are interested in reaching out to him, just let us know. Oh, we got another question. Thanks, Glenn. So how well does this unit work in colder climates?
I mean, that's the thing. They are rated up to minus 25 degrees centigrade. But again, let's move it to the our presentation side. Yeah, it can do up to minus 25 without any issue. But again, if you see here, uh, let's talk. If you're talking about or Toronto weather, if you're saying we are good to run up to, let's say, minus 5. Like, issue is you it on a like a straightforward answer. Yes, it can do up to minus 25 degrees centigrade. That's the first thing. But second thing, do we need to run it minus 25? That's a question, because we have a flexibility, because we are not directly supplying hot water from the machine to the facility. So what is happening there? We are charging it. We are charging a hot water tank that is supplying hot water to the building. So we have a liberty at what time we want to charge it. So either we can use it, use if your temperature is good, you can use it like a night time where you have got a good electric rates. You can use this run the machine there, or if you have like a lower temperature, like reaching minus 25 or something, we 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 do not want to run it minus 25. We can run it in a temperature which is conducive to us, and then charge it, and we don't run it on minus 25 centigrade.
All right, I had another question here. Nathan says, I know that this was about domestic hot water, but do you know if people are using them for cooling server rooms at all?
No, this is a hot water only. It's for hot water only, not for cooling purpose. Definitely not.
Okay.
Because server room cooling is a different machine, yes, but it's for heat pump hot water, the sanitary hot water that can be used for domestic use. That's a major one.
Okay. All right. Any last straggling questions to come in from some of our lovely attendees? All right. I'll give you 20 more seconds and then it'll be 15 minutes prior. And then anybody on our presentation can have a little bit of a break before they join in on our next one. So I'll give it, I will, Nathan says, okay, thanks. All righty. All right. If nobody else has any questions, Glenn also says thank you.
Thank you. Thank you.
I'm going to wrap it up now, guys. You guys can have a little bit of a break before you guys join in for the next session. So again, I want to thank you, Kashif, for that fantastic presentation, and thank you, everybody, for joining in. So for our commercial side of things, our next presentation is going to be on benefit of using VRF systems in commercial and residential applications by David at LG. Oh, okay. No, we can still answer some questions. So we do actually have some more stragglers, so I don't have to wrap it up quite yet. So Micah is asking, is there an easy way to compare the efficiency with a conventional machine?
Yeah, it's easy, like a conventional machine that you want to compare it with a boiler or something, or how, or electric heat, how, which is conventional, like electric versus gas heating?
I'm not sure.
I assume so.
Micah, if you want to jump into the chat and let us get it clarifying what you're looking for in terms of what a conventional machine is. Kashif will answer there. While we're waiting for that, we'll jump back to that question then, to give you some time, Micah, but we'll jump to Stephen's question. So he also he asked if we would like to get additional training on this unit, who do we reach out to?
Stephen, you can contact me. I'll connect you if for our tech team. If you're using a hands-on training kind of thing, I can connect you with the relevant people. They can help you with this.
Okay, wonderful. I will make sure that you guys are able to reach out to each other following today's technical training day. So Micah did clarify his question as well. So he says gas heater versus heat pump.
Yes, there's not a straightforward way, yeah, but you can use it. I have done it. There's a way that you can do it. You convert like a thermal energy into equivalent energy that is used by the electric machine, and then you can compare it. It's not straightforward, but yes, it is compared. It's comparable. Definitely, it's comparable. That's the reason we concluded that okay, so this is the way we did it. Like with a gas fired, yes, we can compare it with the CO2 heat pump. Definitely, it could be done. And if you want to do it any further, I can help you with this one. You can contact me, and we can do it together. We can work it out.
All righty. Any more struggling questions that want to come in? We still have a little bit more time. I had the Jeopardy music. I would do that in the background right now.
Yeah.
All right. Well, I'll do my little wrap up again. If any questions come in, again, I'll take a stop and we'll answer the questions. So again, thank you everybody for joining in on our first commercial session of the day. So our next one's going to be on benefit of using VRF systems in commercial and residential applications. That presentation will be by David at LG. So please tune in. Again, to access any of the presentations, you just have to go back to the lobby and you'll be able to find it there. Each and every presentation from today will be living long on our YouTube series after. So if you would like to go back and review any of the topics that have been talked about today at our Heat Pump Technical Training Day, they live long and on for every single person here. So thank you. All right, I'm going to stop the broadcast. Please, everybody, go in and join our next session. Take a little bit of a break, and we'll see you in later.
Thank you.
Thank you.